All right, now we move on to the energy section, and I believe this is page 6 of the practice test, so I'm going to go ahead and take a look at some of the work here. So I kind of start off with a couple of, hey, use the basic formula and solve, and then we kind of move into more advanced work where we have a full energy kind of longer problem, kind of a scenario to solve. So first, we have a kinetic energy of 200 joules. We are given a mass and we want to know the cart's speed. I'm using the energy formula, so I'll actually write down that EK equals 1/2 mv squared. And from there, I'll just plug in my energy. I'll have 1/2 times my mass. I have v squared right here. And then I can go ahead and actually isolate v. I believe that's going to be the square root of 50. But let me just verify that. Yes. And so that'll be, yeah, the square root of 50. And when we actually isolate that, that should be around 7.1, but let's just verify. Yeah, 7.1 meters per second. And in fact, I'll write that right here. So 7.1 meters per second when we solve. Now for the next scenario, we have a spring that's compressed to 2 meters. One thing I always get on these elastic energy problems, I just want to clarify a couple things now because this comes up a lot. I think with potential or with gravitational energy and with kinetic, it's pretty clear what things are. So just a little clarifier here. Let's remember that K is the spring constant. And the units of that are newtons per meter. And then X is the letter we use to keep track of the compression or the stretch. So to that end, I'm going to go ahead and plug in these numbers. So I'll say 1,000 is going to equal 1/2 times K times the 2 squared here. And so when I actually isolate this, I'm going to end up getting K is, let's see, 2,000 divided by 4. That's going to be 500 newtons per meter. And I'll actually just copy that right there. Next, we have this mass raised to height above the ground. We have a second mass raised 3 times the original height, and we're trying to compare these two energies. So again, let's kind of talk about mass 1, mass 2, and label things carefully. So for mass 1, its gravitational energy is going to be mgh. Now, mass 2, it has 3 times the original mass, and it's 4 times the height. So what that tells us is that we get 12 mgh when we compare. So the ratio is going to be 12 to 1, like that. Now, number 18, I'm not going to use the bar graphs because it seems that people are okay with kind of going directly to the equation. You don't get points for using them, though they may help you clarify the problem. You know what, since I'm kind of using this to sort of teach and illustrate, I'll draw them, but they're not required. So we have this box being launched into the air from a spring. And the idea here is that we have the elastic energy, and then that gets converted into gravitational and kinetic, like that. Because we have a speed greater than 0 and a height greater than 0. And here, that's the 0 point. So we have V and H equal to 0. And all our energy stored in the spring. So we're going to have E elastic equals gravitational and kinetic energy combined. When we put these numbers in, we're going to have mgh plus 1/2 mv squared. And that's going to be 2.5 times 10 times a height, which is 10, plus 1/2 times 2.5 times 4 squared. And I'm sorry, the height here is 6, not 10. There's the h. So keeping all that in mind, the elastic energy is going to work out when I actually calculate that number. Let's go ahead and get that down. That's going to be here. We'll do 2.5 times 10 times 6 plus our, and that's getting me 170 joules. Next, we want to get the spring constant. So here we will use that elastic energy of 170 joules to determine the spring constant by setting it equal to 1/2 times k times 4 squared. Let's remember that this is the letter x and spring constant is the letter k. So we have 340 divided by 16 equals k. And when we work that out, that's going to give us a k value of 21.25. And the units on that, whoa, are newtons per meter. And then for the very last part here, we have the spring dissipating some energy, and it only has this speed at the end. We're going to determine that dissipated energy in the following manner. So we're going to take that elastic, and now we're going to set it equal to the three energies that we encounter when it's in the air, which are gravity, kinetic, dissipated. And we're going to have here 170 gets transformed into 2.5 times 10 times 6 plus 1/2 times 2.5 times only 3.8 plus the dissipated energy. And I'm sorry, we need to square that speed. So when we finally isolate the dissipated energy, we will end up getting 18.05 joules, if I'm correct. I'm going to double check that answer right now, just to make sure it makes sense. So, yes, 170 minus 2.5 times 60. That gives us the 20 joules. And then we're going to have 1.25 times. So it actually looks like our dissipated amount of energy is going to be a simple 1.95 joules dissipated when we're done. All right.